A major challenge in the design of field robotics is real-time adaptation to physical changes of the robot due to damage, variable payloads, or other unforeseen situations. To address this issue, we have been studying the adaptability of ophiuroids, an echinoderm related to starfish. Like their cousins, they possess 5 functionally interchangeable arms that diverge radially from a central disc. Due to the radial symmetry of their body structure, ophiuroids are able to move in any direction. For example, this ophiuroid chases the chemical scent of his favorite food, dried shrimp, without first turning towards it. An interesting aspect of ophiuroids is their ability to autotomize, or self-amputate an arm in order to escape from predators. Surprisingly, the animal is able to continue with little loss in performance after almost arbitrary amputation. Despite such remarkably adaptive ability, ophiuroids have a relatively primitive nervous system with no central nervous system. Instead, radial nerves run along each of its arms, joined to a circumoral nerve ring. So how is this simple system capable of exhibiting such highly adaptive and resilient behavior? To answer this, we focus on the inter-arm coordination mechanism by analyzing the resilience of locomotion when different combinations of arms are fully amputated. In order to simplify analysis, the remaining arms are trimmed to relatively short stubs. This allows us to focus specifically on the inter-arm coordination mechanism, as each arm can only generate propulsive forces in a single, easily identifiable manner. In each case, the animal was able to coordinate its remaining arms to move effectively, even after almost arbitrary amputation. We then constructed a simple mathematical model to explain the experimental results. First, the moving direction is determined by a chemical stimulus, such as the scent of food. Then, each arm begins to move at random, which generates contact forces by interacting with the environment. This sensory feedback is then used in a decentralized manner by each individual arm. If the contact force assists in propulsion towards the desired direction of motion, the arm continues with a long propulsive stroke, followed by a recovery stroke. On the other hand, if the contact force impedes the desired motion, no further action is generated. Our model was tested with a robot, mimicking the arm-trimmed subjects used in our behavioral experiments. The desired moving direction of the robot is controlled remotely to simulate an external stimulus. Each arm of our robot has a vertical and a horizontal rotational joint, actuated by servo motors. The decentralized reflex controller is then implemented to simulate our model. The robot is indeed able to move in the desired direction in a manner remarkably similar to the actual animal. The robot is able to move even when various limbs are amputated, for example with only 4 arms, 3 arms, 1. Just one arm. All without changing or retuning the control program. Our findings will help develop more resilient and adaptive robots that can assist in human inaccessible areas such as during disaster response, as well as help us understand the essential mechanisms underlying resilient animal locomotion.